Okay, in this problem we have a 3 kilogram ball that is attached to a cord of length L, which is 500 millimeters. The ball rotates in a horizontal circle as shown with a constant speed of 2 meters per second. One thing we're interested in is the angle theta that the cord makes with the vertical. We're also interested in the tension in the cord. So let's draw a free body diagram of the situation. Let's show a schematic representation of Newton's second law and show a free body diagram on the left hand side showing all external forces and equate that with the mass acceleration diagram on the right hand side. So let's draw the forces acting on the ball. One force is weight or mg in vertical direction. Another force is the tension in the cable or the cord, which makes an angle theta with vertical. So let's show that angle here. And these are the only forces acting on the ball, assuming air resistance is negligible. On the other side, I will show components of acceleration. Due to the nature of geometry of the situation, I choose to go with the NT coordinate system. So normal acceleration is pointing towards center of rotation, therefore I have MAN in this direction, and in general tangential acceleration is tangent to the circle MAT. Now let's also show the vertical direction by y-axis. There is no acceleration in y or vertical direction. Since it is stated that speed is constant, recall at is dv dt, therefore at is 0, so this component is 0. Then, since there is no vertical motion, I can write net forces in y direction equals to 0, and from the left FBD I can write t cosine of theta minus mg equal to 0, or I can rewrite this as t cosine of theta equal to mg. Let this be called equation 1. Now I can write a second equation in normal direction. Net force in normal direction equals to MAN. Let's choose positive to agree with the direction of AN, and observe that AN, recall from kinematics that AN is V squared over radius of curvature. Note that radius of curvature is the same as radius of the circle, which I label rho, and observe that rho is opposite to theta, therefore rho is L sine of theta. So if I write this equation in normal direction on the free body diagram, I see that the normal component of force, the component of tension, is in normal direction opposite to the angle theta. Therefore, left side of this equation is t sine of theta, and right side of this equation is mv squared over rho. Let this be called equation 2. Now, since I'm interested in finding the angle theta and there are two unknowns, one being tension T, the other being angle theta, I eliminate tension T by dividing equation 2 by equation 1 to eliminate T. Then this gives me T cosine of theta divided by I'm sorry, I should say t sine of theta. T sine of theta divided by t cosine of theta, since I'm dividing 2 by 1. And that equals to mv squared over rho divided by mg. Observe that m cancels out, t cancels out, and this equation can be simplified. If I plug for rho, let's go to the next page. I can have, so plugging for rho, I simplify the previous equation, and I will have sine of theta over cosine of theta equal to v squared over, if I plug for rho, I have gl sine theta. Now, to take this equation out of its fractional format, I cross multiply and rewrite the following. Rewrite the equation as gl sine squared theta equals to v squared times cosine of theta. So now I have an equation with one unknown in terms of theta. Since I have sine squared and cosine, I plug for sine squared. I use the trig identity, sine squared theta equal to 1 minus cosine squared, to turn the equation into the following. So the left side of the equation is going to be gl times sine squared, which is 1 minus cosine squared theta equal to v squared cosine of theta. Observe that this is an equation which is in quadratic format. If I plug in for the given values, g is 9.81, length of the cable is 500 millimeters or 0.5 meters, times 1 minus cosine squared theta equal to speed of 2 meters per second squared, which gives me 4 cosine of theta. If I simplify this equation and throw everything to the left hand side, I will have the following: cosine squared theta plus 0.8155 cosine of theta minus 1 equal to 0. So this is a quadratic equation in cosine of theta. If I use the quadratic formula, cosine of theta equals to minus b plus or minus square root of b squared minus 4 times a, which is 1, times c, which is minus 1. The whole thing divided by 2a, which is simply 2. Solving this equation, we obtain two solutions. One gives us cosine of theta equal to minus 1.49. Second solution is cosine of theta equal to 0.672. Of course, the number bigger than 1, cosine of theta, can't be outside of the interval minus 1 to 1. Therefore, this is an extraneous solution. The only solution is cosine theta equals to 0.672, which corresponds to, if you solve for the angle, it corresponds to an angle of 47.8 degrees. Now, continuing to the next page, if I let's see, if I use the first equation, which was, if I use the first equation, which was t cosine of theta equals to mg, now that I have the angle, I can solve for tension T. Mass was 3 kilograms times 9.81 divided by cosine of 47.8, and this gives us a tension of 44 newtons.